So there's good news and bad news with Kirchoff's rules. And before we answer that, we better open with prayer. Father, we thank you for this morning. We thank you for a spring break coming up. And we pray, Father, for the rest and the refreshment that we need. We pray for safety for our friends who are traveling. Pray that you bless the robotics team this morning in the competition. Help us, Father, to give you our best even on the last day of third quarter. In Jesus' name. Good news, bad news. We'll do the bad news first. This is some of the hardest stuff that a first-year college physics class has to learn. They're some of the hardest, most time-consuming problems in first-year college physics. But the good news is, because these Kirchoff laws problems take so long, you generally never see them on an AP Physics test or an AP Physics exam, because it would just take too much time to do it. Though they might have some questions where you set it up, or they might have some questions based upon the two fundamental principles that Kirchoff's law is based on. So, what are these rules, and what makes these circuits complex? Kirchoff's rules apply to a DC circuit, so you've got a regular power supply like a battery. You don't have alternating current. Number two, what makes it complex is not so much all the different branches and resistors you might have, but what makes it complex is you might have multiple energy sources, multiple power supplies, multiple batteries, instead of just one in the circuit. That's what makes it a little bit more complicated. Now, the two rules are based upon conservation rules. The first rule says when we look at junctions, a junction is where multiple wires join together, or one wire goes into multiple tributaries, so to speak. A junction rule basically says the current coming into the intersection must equal the current exiting the intersection. And Max is saying, oh, so I see, interesting. And of course the logic here is, just like at an intersection when you're driving, you hope that all the cars that enter the intersection eventually leave the intersection. In other words, you never come to an intersection and cars just disappear. Nor do you come into an intersection and cars begin to pile up, unless of course the stoplights are out. But eventually the tow trucks come, and all the cars that enter an intersection leave the intersection one way or the other. The same is true here. The intersection rule says that the current coming in must equal the current coming out. And you might say, duh, but you'll see how we use this rule in a little bit. It's, in a sense, it's like the conservation of charge. All the charge coming in must equal the charge coming out. The second rule is a little bit trickier. The second rule says that the sum of the potential differences as you go around the loop must equal zero. It's sort of my plumb tuckered out rule. All the energy in must be used up when you come out the other end. You can't have an accumulation or a disappearing of energy for no apparent reason at all. It's sort of like a conservation of energy rule, but it's energy per charge that's applied to the loop. So we have the junction rule for the current, and we have the loop rule for the voltage. Those are the two rules. Now when we break those rules down, particularly the voltage rule, when we break down the voltage rule, we are going to approach it like this. And my language is going to seem a little bit strange until we actually work a Kirchoff's law problem. As you go around the loop, applying Kirchoff's rules, anytime as you apply the second rule, you are going through a loop and you encounter a resistor. So I'm going through a loop in this direction, okay? And I encounter a resistor. If I'm going with the current in that loop, and you might say, how can you go against the current? You'll see. But if I'm going with the current in the loop, and I come across a resistor in the way, I'm going to use up energy. There's going to be a drop in my energy. I'm going to use up voltage, so to speak. I'm going to have a negative voltage. If I have 20 volts coming in, and I use up 5 volts to get through the resistor, I'm now down to 15 volts at the other end. Kind of logical. Now here, if I'm going with the current, against the current, and you might say, how can you be going against the current? You'll see when we do a problem. If I'm going this direction, and I'm going against the current, and I encounter a resistor, then I have to change the sign. It's like I'm adding voltage. I have an increase in voltage. Now, I already said what makes some circuits complicated is having multiple energy sources, multiple power supplies, multiple batteries. So, again, if I'm going through a loop, you'll see why we do that again in a minute. As I'm going through a loop, and I encounter a battery in the way, and I encounter the battery with the negative first, and then the positive, well, that's what batteries normally do. You arrive at the battery plumb tuckered out, so to speak, and the battery pumps you up, gives you a shot of energy, and so therefore you're going to add your voltage. Whatever the rating of your battery is, you add your voltage there. However, if going through the loop, I encounter the battery hooked up in the opposite direction, I'm trying to come in the positive and go out the negative because of the way I've chosen to go through the loop, well then that's going to be just the opposite. That's going to be a negative voltage. Okay? Thank you. Now again, we've got to do the problems to see why we did, or we came up with these assignments for whether my energy is going to be a drop per charge or an increase per charge. And that is summarized in the red box here. Those things are summarized in a red box. And this almost looks kind of like how I used to look when I had a beard and more hair. But again, receding hairline, facial hair. This picture here doesn't look quite as much like me as mentally it does over there. Have you ever looked at that periodic table over there? That is scary. So, we are going to apply Kirchoff's rules to two different problems. Now this problem right here, you would never use Kirchoff's laws to apply this rule to solve this problem. Because you could do this without Kirchoff's rules. But for the sake of comparing it to the answers you would get in the conventional way, we're going to apply Kirchoff's rules to a simple problem, and then we're going to do it to a complex problem, and then we're done. Okay? For the day. Dress code. So, this problem here, if we were going to do this problem, there's only one battery in here. The regular rules would apply. You could take the two resistors, find the equivalents, add them together, find your current, no big deal. But let's apply Kirchoff's rules. Now, in order to apply Kirchoff's rules, you need to pick loops. How many possible loops are there in this diagram? How many different ways can you take your pencil, start at one place, and work your around all the way through and end up at that point again?
3.
There are 3. For example, there is this loop right here in black. Everybody see that loop? There's another loop that's this loop. Go over the top instead of under. And then there's a third loop where I just do the box. Do you all see that this diagram technically has 3 loops? And all we need are 2 of those 3 loops to generate the equations necessary to solve the question about the currents in this circuit. So far, so good. Now, you can see that the problem, that the way in which your textbook solves this problem is they pick the loop down here and they pick the loop in the box. So let's do it a different way and see if we can come up with the same answer. Let's do it a different way, okay? So, Max, do you have which loop would you like us to use?
Do the smallest one.
The smallest one, just this one right here?
Yeah.
They use the smallest one as well. But you know what? Since they're going to go this way, let's go this way instead. They're going that way. We're going to go that direction instead. We're just going the opposite direction that they pick. Doesn't matter what direction you pick. If you come up with a negative current, you know that your assignment back at the beginning was wrong. No problem. What other loop should we use? Rachel, would you like to pick another loop?
Like around and then on the top.
Go over the top, okay? So the loop that we're going to pick there is in green. We're going to go over the top because I think they went down below. And so now we've picked our 2 loops. And you'll notice that, which direction would you like to go in the loop? They went the logical way, positive to negative. They went this way. So why don't we go the other way, just to be obstinate? All right? In other words, we'll be like Jake. This is the way. We're going to do it some different way. So I just woke him up. So we're going to go this way. Yeah.
To correct?
Hang on, let me go through the lab, just so I go a different way.
Very good. We're going to go this way here. So, the next thing we have to do then is, now that we've chosen 2 loops, we've arbitrarily chosen directions to go through the loop, and now we are going to use Kirchoff's rules. Now you notice we have a junction here and a junction there. Let's first of all do Max's loop, the red loop. We're going to do Max's loop, and we are going to generate some equations. In Max's loop, let's call this current I, let's see. In Max's loop, we have a junction here, and we have a junction there, and so, I need a better red. We want to talk about the current coming into each junction and the current going out of each junction. So let's just call, I'll try to use the same letters that they did so you can compare. So this is going to be I3, which is what they're using. This is I2, and this is going to be I1. So what can we say is true about the current at this junction right there?
I1 minus I2 equals, or sorry, that's I3 minus I2 equals I1.
I3 minus I2 equals I1.
The loop isn't it going the other way?
Well, we're going this way. So we have I3 coming in. Some is going to go that way into I1, and some is going to go into I2.
Sorry,
right?
I thought we were doing this.
So I3 is going to equal I1 plus I2.
If we have the loop going there. Never mind, it's I1 or I3 plus I2.
So if I call this I3, because they did, and I want you to compare, I3 is coming here, we hit the junction. Some of the current goes this way, which is going to be I1, according to the way they designate it, and some is going to go that way, some is going to go that way. So far, so good. Now, let's come over here to that junction right here. This junction, if we're still following our designation, not the books, my I2 comes into the junction right there, and that's going to equal I1 plus I3. Something's not ringing true here.
Can you draw the loops back in? Our loops are different from their loops, so it's hard to see.
I was thinking that we would do this loop right here.
Well, like the flow of our current. And is our current going in the direction the arrows show?
Pardon?
Is our current going in the opposite
No,
direction?
we're trying to go in the opposite direction that the book chose.
Okay, then the first one should be I3 plus I1 equals I2. Because
So
the
here's
current
my
is flowing
I3, and
the current is actually flowing in from I1 because we have the loop reverse.
okay, we have to pick. Yeah, the other thing we have to designate is what direction are we going to assign the current in the outer loop.
I think we
weren't
assigned it to go
consistent here.
counterclockwise.
That's the problem, we weren't consistent. So let's say that we chose this way and this way, okay? So I3 comes into the junction, and some goes out I1, some goes out I2. And now when we come to the other junction, there's our problem. When we come to the other junction here, it's coming in, right?
So that's I3 plus I2 equals I1.
So yes, so there we have I2 coming in, I3 coming in, and I2 and I1 coming in, and I3 coming out. So we have the same equation. So we have, this is I2 coming in, and I3 is coming in.
No, I3 is
I1
going
is
out.
coming in, and I3 is leaving. So we have two equations that are identical at each junction. That's what it's supposed to be. So there is the application of the junction rule. The junction rule gives me one equation, I've got three unknowns. All right, now let's do the talk about, and this is for loop 1, and then later we'll do loop 2. Now let's go through loop 1, the one that we picked, Max's loop, and let's evaluate the energy as we go through the loop. We can start anywhere we want, it doesn't matter in the loop. We're going to do a 360. Where should we start? You want to start at one junction and go around the other way? It won't make any difference. If I'm going to start right here, and I'm coming this way, and I'm coming this way, I encounter a resistor, the 9 ohm resistor. Now, because I'm going with the current, remember we chose to go from left to right across the bottom here, and then right to left across the top. Since I'm going with the resistor, I am going to have an energy loss of IR. Energy loss of IR, which is going to be negative I3, that's the current down here, times the resistance of 9 ohms. And now I'm coming up here, nothing, nothing, nothing. Here's another resistor. Here's another resistor, and that's current I2. And we're going to be using up energy because we're going with the flow of the current times a resistor of 5. And the sum of the energy in that loop has to equal 0. That was the hard one. No matter where I start, when I go all the way through the loop, since in our example, we happen to be going with the current. So when you go with the current, you use up energy when you go through the resistor, and the total energy has to equal 0. So now you can see I have a negative 9I3 minus 5I2 equals 0. So now I have two equations, but three unknowns. I need three equations if I have three unknowns. Remember that? So now I've generated two equations so far. Now let's look at the other loop. And in the other loop, we decided that we were going over the top, weren't we? Which way were we doing? We were going this way, weren't we? So current there. So I have to be consistent. So in this loop, we were going
Current out there.
this way. So let's do this is also loop 1. Now let's do loop 2. Let's do a current analysis at my two junctions. Do you see that in this outer loop, I'm going to get the same equation. If I choose to go this way across the outer loop and I hit that junction, I'm going to get the same equation as I have up here. It won't change. Yes, no? But when I apply the energy to this loop going across the top, we need to have a starting point. How about if we start at the battery? We can start anywhere along here as we go over. Let's start right there. That's our starting point. Okay? And we'll pick up that 6 volts when we come back to it. So we're going this way, no energy, no energy, no energy. And now I encounter a 4 ohm resistor. And that 4 ohm resistor, I'm going with the current. So since I'm going with the current, which was established way back at the beginning, since I'm going with the current, that is going to be a loss of energy when I go through the resistor, according to the rule. And so my current there is I1, and the resistor is 4. And it's going to be negative because we're using up energy. Now we're going to go across the top, and now we encounter a 5 ohm resistor. And my current in this branch is I2. So we have I2, and the ohm resistance is 5. But look at this, everybody. I am going against the current here. We established that the current is going that way. I'm going in the opposite direction. So instead of having a negative sign, I have to have a plus sign. Coming along there, nothing, nothing, nothing. And then I come to 6 volts. I'm coming in the negative, coming out the positive, which means I pick up 6 volts. 6 volts, and the whole thing has to equal 0. So you'll see now I have 3 equations and 3 unknowns. And now you can do matrices if you like matrices. Or you can look at the 2 equations which only have, notice how this equation only has 2 currents and this equation has 2 currents. You can solve both of these equations. You can solve them for I3 in terms of I2 and I1 in terms of I2 and plug them in up there. Does that make sense? So for example, if this equation right here, I could say it's going to be negative I2 times 5 is going to equal I3 times 9. Trying to simplify. And then I would divide by 5 and divide by negative 5, and so I2 I can solve this equation either in terms of I2 or I3 and plug them in up here. And I can solve this equation either in terms of I1 or I2 and plug it up here. I think what we would probably want to do is solve this for I1, which will put it in terms of I2 and plug it in up here. And solve this one for I3, which would put it in terms of I2 and plug it up there. So I3 then is going to equal negative I2 times 5 divided by 9. This is going to come up here. And down here I'm going to solve this for I1. So I1 is going to equal 5 times let's see here. Might be easier if we do this. We have 5I2 plus 6 equals 4I1. And then if I divide by 4, there's my I1. And then this term can come up here for I1. And now I have everything in terms of I2. And I can solve for I2. Pretty complicated. If when I solve for I2, I get a negative current, and I know my original designation is backwards, and I just change it. I don't have to do any more math, I just redraw the diagram, showing the current in the right direction. Once I know I2, I can plug it in here to find I1. And once I know I2, I can plug it in here to find I3. Now you can see this is a whole lot of work, very complicated, for a very simple circuit that doesn't need Kirchoff's rules at all. So let's look at one that's a little more challenging. What makes this one challenging is you've got a power supply there and a power supply there, a battery. So why don't we solve this problem the same way that they did it? So now I'll walk you through it. So how many loops do we have in this picture right here? 3. We have the big loop, we have the top loop, we have the bottom loop. And we can choose to go any direction we want for any of those loops, and then apply Kirchoff's rules. So let's look in your book. What loop are they going to do? What are the loops that they do in the book? I don't even remember the problem. Anyone see? Okay, well, let's not worry about it then. We'll just do it our way. So, pick a loop. Jonathan, pick a loop. Which loop would you like?
Smaller bottom.
The bottom loop. Okay, so we're going to do the bottom loop. All right. Alyssa, would you like to pick a loop? The top loop. So we're going to do the bottom loop, and then we're going to do the top loop. Now, in the bottom loop, we need to designate the direction of the currents. If we choose the wrong direction for that current, our answer will come out negative, and we just say, okay, it goes the other way. So, Alyssa, would you like to choose the designations that they are choosing right here for the bottom loop?
Sure.
Okay. So, right here, what equation can we generate using the junction rule for that point right there? Current coming in must equal the current coming out. Do you see that I1 plus I3, I1 plus I2 equals I3? Do you see that there? I1 plus I2 equals I3. So there's an equation. Let's look at the other side then. And this current is going this way and this way. and it's going that way. So, what equation do I get at this point for the current? Apply the junction rule at this point, Tom. What do you get? Here's I3 right there. This is all I3. This is all this is I2. So this is I2 right there. And through here, this is I1. I1 is right there. So what is my junction rule? What equation will the junction rule give me applied to this point?
Then I'll be the same.
Yeah, it would be the same. I3 is coming in, I2 and I1 is coming out. I3 is coming in, and I1 and I2 are coming out. That's pretty typical. The junction rule at each of those two places is the same. So I don't pick up any additional equations by applying the junction rule. Okay? So we need two more equations then, don't we? Two more equations. So the first equation we're going to generate is applying the second rule, Kirchoff's rule, to we pick the lower loop, right? And then we pick the upper one.
Yeah.
So let's apply the junction rule, and you can start anywhere you want, but let's start right there. We're coming down here, we're going with the current. You all see that we're going with the current. And now we encounter a resistor. And so I'm going to have a voltage loss of IR. And the voltage loss is going to be I3, that's the current, and the resistance is 2. Okay? So my energy is IR, current times resistance. I keep coming, come across here, turn the corner, and now I'm entering the battery in the conventional way. Coming in the negative, going out the positive. So I'm going to pick up 10 volts. Remember, volts equals IR, so this represents volts. This represents volts. So I'm picking up 10 volts, keep coming, and notice I'm going with the current across I1 through my 6 ohm resistor. So again, that's going to be negative I1 times 6 ohms, total equals 0. Everyone see that? So what do I have here? I have a negative 2I3 plus 10 plus or minus a 6I1 equals 0. So there's my next equation. I've got one equation, two equations, I need a third equation, and the third equation will come from applying the loop rule to a different loop. So this time we want to do the loop rule across the top. And it doesn't matter which way you go, so which way would you like to go in this? Shall we go clockwise?
Sure.
Want to go clockwise? All right. So where do we want to start? Can we start in the upper left corner?
Sure.
Being Americans, we'll start in the upper left and work the way around. Okay? So we're going this direction. We are going with the current, with I2 in this direction. So I'm starting right there. I'm coming through here. Now I'm entering the battery backwards. If I enter the battery backwards, that's going to be a negative voltage, negative 14. And now I keep coming, no resistors turn the corner. And now I encounter a resistor, and I'm going against the current. I1 is going this way, but since I'm going clockwise, I'm going against the current. And so instead of being negative like it is up here, it's going to be a positive. Current times resistance. The current is I1, the resistance is 6. And then I come to the battery, and I'm coming in the battery through the wrong direction. I'm coming in the positive instead of the negative. So that's going to be a loss of 10, all equals 0. And so if I simplify this equation, you can see that I get 6I1 equals 24. If I add the 14 and the 10 to the other side. Okay?
Don't we have to
Wait a
get the
minute, do I-
resistor as well?
Oh, I'm not done yet. My bad, thank you. I thought that looked too easy. So we're here, I haven't finished, now we hit the resistor. And as we hit that resistor, we're going with the flow, with the current. So we're going to lose a IR. And what we lose is the current in this branch is I2 times the resistor of 4. And that equals 0. There we go. And so when we simplify this, we have 6I1 minus 4I2 equals 24. And there's my 3 equations. So far, so good. And now I can do matrices, where I can solve this equation for one of the variables and this for one, and plug them up here so that I have the same variable all the way through. And once I get the first current, then I can solve for the other two. If any of them were negative, then I knew I drew the arrows in the wrong direction. So you can see that we just spent, I don't know, close to 35, 40 minutes just doing 2 problems. And we didn't complete the math. I left the algebra to you. Now, be honest, anybody not know where to go from here? How many of you would solve this using a matrix? Anybody use matrix? Where you'd have 6 minus 4 minus 24 equals 0, and negative 2, let's see. Oh, you'd have to put all of this in terms of I1, I2, I3 minus or plus the constant equals 0. That's how you put them all in the same form, and then you'd solve the matrix. Most of you then would use substitution. Okay? Any other questions on this? Well, why don't you take 5 minutes, the rest of class time, solve those 3 equations for the 3 currents.
Just on the left.
Pardon?
Just on the left.
Yeah, the one on the left. And see what answer you get compared to the book. And if we did it right, if I did it right up there, and if you do it right, you should get the same answers. Go ahead.